Hello everybody, today we're looking at 10.2, which is vectors in space. And it's going to be another really easy one because vectors in space behave identically to vectors in two dimensions. Much like any other part of what we were just talking about in the last section, whether it be midpoint formula or distance formula, things like that. They all have the same basic idea. You're just extending it into the third dimension. So vectors are not going to be any different. So we kind of just have to add a little piece to the notation. Before, we would have, when we were writing things in forms of linear combinations, we would have a number in the I direction, a number in the J direction, which would be like so much along the X, so much along the Y. But now we have to extend it in the direction of Z, so much in the X, so much in the Y, so much in the Z direction. So I, J, and K are the unit vectors in each of those directions. I is a unit vector on the X, J is a unit vector on the Y, and K is a unit vector on the Z. Okay, so just adding one more piece of notation there. And after that, it's pretty much smooth sailing. All of these different formulas that we used and all of kind of the theorems or ideas that we had all are still true. Two vectors are equal if their corresponding components are equal, regardless of if it's two dimensions or three. The magnitude is still going to be the square root of each of the terms of the component vector squared and taken under the square root. A unit vector will still be the component over the magnitude. The sum will be the same. Normally you would add the first terms together, you'd add the second terms together. Well, now because we're in three dimensions, you also add the third terms together. Alright, so we have the first terms, second terms, third terms, all added together in order to combine two vectors. When you're doing some sort of multiple or scalar multiple, again, you just multiply to each term. Before, all we would do is multiply to the first and second. Now that we're in three dimensions, we multiply to the third. And then something a little bit more complicated like the dot product, probably one of the more complicated things that we did, which the process of it wasn't too bad. It was take the first term of each, multiply them, take the second term, multiply them, and then get the sum of those two products. Well, the same thing is going to be true here. We're going to take the first two, multiply them, second two, multiply them, and now that we're in three dimensions, third terms, multiply them, add it all together. Alright, so basically, if you're looking for something common between all of these things, it's just that the formula is exactly the same, the process exactly the same, with the exception of one extra step, and that's moving it into the third dimension. Alright, so we're not going to do an example of all of those things. I think that'd just be a little bit tedious. So I just want to do, two or so, just to show how it works, and that it is indeed identical. So we want to try to find the component form of a vector that starts with an initial point of 342, terminal point 364. So how we would do this normally would be kind of take the initial point and move it to the origin, 0, 0, 0. So we're still going to do the exact same thing. We're just going to do it in a way that kind of keeps things a little bit simpler. So I'm going to take the terminal point, 3, 6, 4, and I'm going to subtract each of those things, 3, 6, and 4, and I'm going to subtract the initial point. And what that does, mathematically, is it moves the initial point to 0, 0. And some people were doing this in two dimensions, which was good. Other people, would maybe draw it out and move it and then see where the terminal point ended up. If you were already doing it this way, it's going to seem a lot simpler for you. If you were not, hopefully it's not a big deal to move into this, because drawing it out in three dimensions can get difficult and confusing sometimes. So keeping it numeric isn't always a bad thing. So now there's a little bit more. Once we know that the component vector is 0, 2, 2, we want to figure out a unit vector in the direction of v. Okay, so in order to find the unit vector, I need to divide the component by the magnitude, right? Because it's a certain vector over that vector's magnitude. Right? So if this is our vector, we need to figure out what the magnitude is. So the magnitude of v will be each of the components squared, added together under the square root. So 0 squared plus 2 squared plus 2 squared, right? So all of that together is going to be the square root of 8, which I can simplify to 2 square roots of 2. And so that is my magnitude. So if I want the unit vector, what I have to do is take 0, 2, 2 as a vector and put that over 2 square roots of 2, which means each of the components of that vector are divided by 2 square roots of 2. Right, so 0 over 2 square roots of 2, that's just going to be 0. 2 over 2 square roots of 2 will be 1 over the square root of 2, which I can rationalize, square root of 2 over 2. And 2 over 2 square roots of 2, again, is going to become square root of 2 over 2 once I rationalize the denominator. Okay, so overall, same process as before. The only difference is a little bit longer because I had this third piece tacked on the entire time. Alright, let's take a look at exercise 11 in the book. And once you're set with that, we can move on to example 2 in here. When we're trying to find the angle between two vectors and looking at dot products and this idea of orthogonal or not, that idea is still exactly the same. Nothing changes with that either. It's kind of just interjected. So the next example is going to be much more difficult, because if you remember, in chapter 6 we had the kind of thing where I had two vectors supporting a weight kind of like this, and it was in 2 dimensions, but it was the same type of idea as this. So again, that problem is going to be the exact same thing, only extended to 3 dimensions, which, something like this was already difficult. Something like this is, just going to take it to that next level. Okay? But for those of you that remember the process, hopefully going through how to solve this won't be too difficult. You all did it on your pre-test, and hopefully you gained a little bit more understanding of it. So when we go through this one, it won't be too bad. Alright, so we have all these different points where the wires are connected, and we have a specific point in space where the weight is getting pulled down. Let's remember that the weight is 480 pounds, and that this point here is 0, 2, -1. I do believe that I've put this picture on the next page where I'm going to do all the work. Yeah. Alright, so these are the points where it's connected. Move this down. And this is our point where the weight is being held, and the weight is 480 pounds, which means that the resultant weight between all of these vectors here has to be 0 in the x direction, 0 in the y direction, and negative 480 in the z direction, right? Because it's not going in any particular way other than down, which is the z direction. So 0, 0, negative 480 is w. Okay, and that's going to be important there. So if we think back to what we did before in 2 dimensions, we essentially needed all the vectors, and we were expressing them as magnitude times direction. Now, if you have magnitude and direction, you have a vector, right? So I'm trying to find the tension in each rope, so I'm trying to find the magnitude. So magnitudes are going to remain variables until the very end. So what I am going to need is basically these different vectors, u, I'm going to call them u, v, and z. And we'll say that u is going to be the magnitude of u times a unit vector in the direction, let's use, let's use this one right here. Okay, so that's going to be u. So what I need is the component form of this vector over the magnitude of that component form. So what am I going to get here? I'm going to get, let's see, 2 minus 0, right? The x's, 2 minus 0. Then the next y's, 0 minus 2. And the z's, 0 minus negative 1. That's the component form of that over the magnitude. That's going to be 2, negative 2, 1, which means the entire thing is going to be 3. Okay, so what this tells me is that I can express this vector u that's being pulled by this weight w as some magnitude times the unit vector in that particular direction, which is going to be 2 over 3, right? The first component over 3. The second component, negative 2 over 3. And the third component, 1 over 3. Okay, so now I have a way of expressing this vector based upon some magnitude that's going to be being given to it by this weight that's getting pulled down in the direction of this unit vector. So we're showing this direction. Alright, so now we're going to do the same thing for v and z. I'm going to change color so it doesn't get too confusing. So v is going to be this one over here. Alright, so I'm going to say it's going to be the magnitude of v. And then I got to start making the components. So it's going to be 0 minus 0. Minus 0. Right, subtracting the x's. And then 4 minus 2, subtracting the y's. And then subtracting the z's, 0 minus negative 1. So now I have the component form of that vector. I'm going to put it over its magnitude. So this is going to be 0, that's going to be 2 squared, that's going to be 1 squared. So that means this entire thing on the bottom here is the square root of 5. Alright, and then I can simplify that and say that it's going to be the magnitude of v times the component form, which means I just need to kind of hook each of these components with the denominator. So 0 over the square root of 5 is just going to give me a 0. 2 over square root of 5. And 1 over square root of 5. Awesome. Almost there. I'm going to switch color one more time. And we're going to do z. And hopefully by now, you might be moving past me. You're doing this a little bit faster. We got negative 2 minus 0. We got 0 minus 2. And we have 0 minus negative 1 again. All over the magnitude of this particular thing. That's going to be 4, 8, and 9, so 3. And I can simplify to say it's going to be the magnitude, oops, that's a v, magnitude of z. The component, which is going to be negative 2 over 3, and negative 2 over 3, and 1/3. Awesome. Now where did we go from here when we were in 2 dimensions? Let's see. Basically what's happening here is I have all of these different vectors who somehow, when they meet at this point, are forming a resultant of w. So somehow all of these vectors are combining being the important word, to w, which is going straight down. Right, so somehow, I'm going to change back to black again. Somehow u plus v plus z equals, in order for this entire system to be in equilibrium, plus W, sorry. Back. Plus W equals 0. So basically what that's saying is that this point right in here, this point where they all connect, is an equilibrium point, meaning there is no direction, there is no magnitude at this point. So when all of those things combine at that singular point, there is, no magnitude or direction, right? Nothing's getting pulled, and it's all in stasis. So, alternatively to that, U plus V plus C equals negative W. Okay, so that's kind of a more theoretical idea to what we're about to do here. What we did in the last one is we said, okay, well, if all of these things have to combine to equal W, well, that means that when I add all of these first terms together, they should equal 0. When I add all the second terms together, they should equal 0. And when I add all the third terms together, they should equal negative 480. Well, because that's the way that we add vectors together. We add their first terms, their second terms, and their third terms, and that gives us the resultant. So, somehow, the first term, which would be magnitude of U times 2/3, that plus the first term of this one, which is a 0, plus the first term of this one, which is the magnitude of Z times negative 2/3. Somehow all of those things have to combine and equal 0. Also, if we look at the second terms, the magnitude of U times negative 2/3 plus the magnitude of V times 2 over the square root of 5, that's this one right here, and the magnitude of Z times negative 2/3 all equal, again, 0. And then lastly, when we add all of the third terms, magnitude of U times a third plus magnitude of V times 1 over square root of 5 plus the magnitude of Z times a third, that should all equal 480. Right? So, I have a system of equations here, which I now have to solve. A system of equations in 3 variables with 3 unknowns. Right? 3 equations, 3 unknowns. And this is why I wanted you to do those 3 variable systems earlier. Because something like this becomes much, much, much harder. Especially with the type of fractions that we have here. It becomes much harder to try and manipulate it without using matrices and without using the elimination process that we talked about. So what I would like you to do to finish up this section is to complete and finish this system of equations. Work your absolute hardest on it, try your best, and when we come into class next time, we will take a look at this and make sure that everybody is able to do it. Alright, good luck with this. Again, just do your best with it. It may turn out to be easier than it looks. Alright, I will see you guys later.